Welcome to the Deep Dive. Today we're tackling something truly mind-bending in artificial intelligence.
Yeah. What's on the menu?
How AI can learn to reason effectively with, well, absolutely zero pre-existing human-labeled data for the specific tasks it's mastering.
Right. The absolute zero reasoner stuff. AZR.
Exactly. Our main source is that fascinating paper, Absolute Zero Reasoner, AZR, achieves state-of-the-art performance with zero data. We'll be, diving into this and some related ideas to really get our heads around it.
And what makes this so revolutionary, really, is the idea of an AI reaching top-level performance in really complex areas, like math and coding, by learning from essentially a blank slate in those domains. It's not being spoon-fed examples. It's figuring things out for itself.
Okay, blank slate that then becomes a reasoning powerhouse. So our mission today is to understand this AZR. How can an AI get so capable without us, giving it tons of labeled info or even telling it what problems to solve?
Yeah, and what are the implications? What could the future look like if AI can learn and reason in this self-driven way?
Right. So maybe first, to really grasp how different AZR is,
Right.
we need to quickly look at the old way, right? How AI is usually taught to reason.
Good idea. The standard method is called supervised fine-tuning, or SFT.
FFT. Okay.
Think of it like this. You're teaching a student by showing them just countless solved problems. And crucially, these problems come with the step-by-step thinking.
The chain of thought reasoning people talk about.
Exactly, that chain of thought and the final correct answer.
Right. So SFT is basically learning by imitation. We give the model lots and lots of examples of how to think and what the right answer is, and it just learns to copy that.
Precisely. For SST, you need these, massive data sets filled with queries, those expert-level chain of thought explanations, and the perfect solutions.
And these are made by humans.
Or usually created by human experts, or actually increasingly by very advanced AI models themselves acting as the teacher. The whole aim is for the model to learn to mimic these expert responses. It's mastering a skill by studying examples of mastery.
Okay, that makes sense. It's like learning, a new language by just studying textbooks and examples of perfect grammar. But AZR, it just flips this whole script, doesn't it?
Totally. The absolute zero paradigm is a completely different ballgame. Its core engine is self-play.
Self-play.
Yeah. Instead of learning from external data, the AI learns by playing a game with itself.
Self-play. Like an AI arguing with itself to learn math. How does that even translate into solving equations or writing code?
Well, it's not quite arguing, it's more structured. The AZR framework sets up two key roles within the AI: a proposer and a solver.
Proposer and solver.
The proposer's job is basically to come up with its own tasks. And this isn't random. The paper says it's conditioned on some internal variable. Think of the proposer as like an internal teacher deciding what the next lesson should be.
Okay, so the AI is designing its own curriculum in a way. But how does it make sure these self-made problems are actually, solvable and have correct answers?
Good question. That's where the environment steps in. Based on the task the proposer suggests, the environment helps refine it into a valid reasoning task.
Refine it how?
It helps structure the question properly, and it also determines the gold or a correct answer for that task. So the proposer has a rough idea, and the environment helps flesh it out into a workable problem with a verifiable solution.
Okay, got it. So the AI essentially has this internal system for creating and validating its own learning material. What happens once a task is created then?
The solver takes over. Its job is to tackle the challenge that the proposer and the environment have set up.
Right. It tries to solve the problem.
Exactly. And once the solver attempts a solution, there's a reward system to evaluate how it did.
Okay. So there's still a way to track progress. What kind of rewards are we talking about here? Not like little digital treats.
Hey, no, not treats, but conceptually similar. The proposer gets what's called a learnability reward.
Learnability reward.
Yeah. Now, this isn't about whether the task was solved correctly right then. It's about how much the solver is expected to improve if it trains on this particular task.
Whoa. So it's a reward for being a good teacher, for designing a good lesson.
Exactly. That's the fascinating part. The AI gets rewarded for being a good teacher to itself. It's like it's identifying its own weaknesses and generating the exact learning material it needs without any human telling it what to study.
Wow. Okay. What about the solver? Does it get rewarded too?
Yep. The solver receives a solution reward. That's more straightforward. It's
Huh.
based on whether its answer is correct. The environment acts like a judge here, verifying the accuracy.
Makes sense.
And there's also this coefficient mentioned, which basically balances the AI's drive to explore completely new kinds of tasks versus its need to get better at the types of problems it already knows how to tackle.
So it's constantly juggling novelty and mastery. Okay. And what's the ultimate aim of all this internal back and forth?
Well, the paper gets into the math, but essentially the goal of this absolute zero setting is to maximize the total rewards, both for proposing useful tasks and for solving them correctly, across all the self-generated learning experiences it creates for itself.
So it's about the AI continuously creating and tackling its own learning curriculum to just become a more powerful reasoner overall.
That's the core idea.
The self-creation of learning tasks.
Yeah.
It sounds like it could get a bit chaotic. How does the AI keep track of everything? Does it just remember everything it tried?
That's where something called the task buffer comes in. During this self-play phase, the buffer acts as both a memory bank and kind of a source of inspiration.
Okay, tell me more about this task buffer. How does it help the proposer, dream up new challenges?
So for tasks involving abduction.
Abduction. Reasoning to find the most likely explanation, right?
Right. And deduction reasoning from general rules to specific cases. For those, the proposer randomly picks a few past successful task triplets from this buffer.
Triplets.
Yeah, a triplet includes the original proposed task idea, the refined query the environment helped create, and the correct answer. These past successes act as examples, like in-context learning, guiding the proposer to generate new, hopefully diverse and valuable tasks.
Okay. It's like looking back at your best work to get ideas for the next project.
Exactly. A great analogy. The AI learns from its own past successes to generate future learning opportunities.
Smart. What about the third type of reasoning the paper mentions? Induction. Finding general principles from examples.
Right. For induction, the process is slightly different. The induction proposer samples a triplet, but this time from the combined buffers of both abduction and deduction tasks.
Okay.
Then the deterministic program from that chosen triplet is presented to the induction proposer, and it then generates a set of matching inputs and a natural language message related to that program.
Deterministic programs, the paper really emphasizes this point. What exactly does that mean for how AZR works? Why is that important?
Good question. In this context, deterministic means that for any given input, the program will always produce the exact same output, every single time you run it. No randomness.
Fuck.
The paper has a formal math definition, but the key takeaway is just that the underlying logic of the tasks it generates is consistent, predictable, like a perfectly written recipe, same steps, same result, every time.
Gotcha. That consistency must be crucial for reliable learning. You can't learn math if 2 + 2 sometimes equals 5.
Precisely. The tasks aren't based on chance, which makes sense if you're trying to build a solid foundation of reasoning.
So what other function does this task buffer serve? You said it helps keep things stable.
Yeah, it plays a vital role there too. Sometimes in a batch of problems a solver needs to work on, there might not be enough valid new tasks proposed. Maybe the proposer messed up the format or something. If that happens, the buffer is used to fill in the gaps with previously validated successful task triplets. It makes sure the solver always has enough meaningful problems to work on, keeping the training smooth.
It sounds like this whole self-play loop, guided by the task buffer, is a really sophisticated way for the AI to build its own educational journey. So, okay, the big question. What were the major surprises that came out of this zero data experiment? Did it actually work?
It absolutely did. And the most significant, perhaps surprising result is that these AZR models showed really strong general reasoning abilities in both math and coding,
Wow.
without ever being directly trained on human-defined data for those specific domains. They learned purely from the tasks they generated themselves through self-play. That's a big deal.
That's just astonishing. It's like learning advanced physics by just, playing with building blocks. Did the starting point matter? Like the initial AI model they used?
Absolutely. The researchers definitely looked into that, how the initial capabilities of the base model influence the final performance. They did an experiment comparing a standard base model variant with another version they called the coder variant. Presumably, the coder variant had more initial training on code.
Okay, so one was maybe better at code to begin with. Did it have an edge in math or reasoning too?
Well, here's the really interesting part. The coder variant actually started with lower average performance in math compared to the vanilla base model.
Lower, okay.
But after undergoing the AZR self-play training, the coder variant ended up outperforming the base model in both math and coding.
Wait, hang on. The one that was initially worse at math ended up being better overall after learning through AZR. How does that work?
Exactly. It's counterintuitive, right? The researchers concluded that the initial coding competency acted as a kind of catalyst within the AZR framework.
A catalyst.
Yeah, it seemed to boost the model's ability to improve its reasoning skills more broadly, including math. It suggests that having some foundational skills in a related area, like coding, can really accelerate this kind of self-learning.
That is fascinating. It implies a sort of cross-domain benefit from this self-play process. This whole AZR approach, it feels very much aligned with how humans learn, doesn't it? You try things, you make mistakes, you figure stuff out. The paper also talks about exploration being key.
Yes, definitely. They explicitly connect AZR to the broader field of reinforcement learning, RL. And in RL, exploring different possibilities to find the best solutions is, a cornerstone principle.
Right. Exploration versus exploitation.
Exactly. But AZR seems to take this idea of exploration a step further.
How so? We're already talking about self-play, generating its own tasks. What's the next level of exploration?
AZR introduces this concept of exploration within the learning task space.
Task space.
Yeah. See, traditional RL often focuses on exploring the space of solutions for a given set of problems. AZR agents, though, they learn not just how to solve tasks, but also what tasks to learn from and how to discover those tasks in the first place.
Ah, I see. So the key insight is shifting from a fixed problem set to dynamically defining and refining the very questions that drive the learning.
Precisely. It's not just about finding the right answer anymore. It's about finding the right questions to ask and explore.
That sounds powerful.
The researchers position this as a powerful new frontier where AI can essentially expand the boundaries of the problems it can even learn to solve.
Okay, so to really understand what makes AZR tick, the researchers did these ablation studies, right? Where they, take apart the system piece by piece.
Yes, exactly. They systematically removed different components of the AZR framework and then observed the impact on performance. They used the 7 billion parameter base model for these tests, and the results were quite informative.
So what did they find? What happens when you start pulling bits out of AZR?
Well, first off, removing induction tasks. Big drop in performance.
Okay, so induction is important.
Very. Similarly, if they relied only on deduction tasks, also a significant decrease. It really underscores the importance of having all three reasoning types, abduction, deduction, and induction, working together in that self-play loop. You need the whole toolkit for robust learning.
That makes intuitive sense. A well-rounded learner needs different ways to think. What about the proposer role itself? Was that as critical as it sounded earlier?
Absolutely critical. They found that if they removed the mechanism that let the proposer learn from those past successful references in the task buffer.
So, taking away its inspiration from past successes.
Right, performance declined. And even more telling, if they completely omitted the training for the proposer role altogether, performance also suffered significantly.
Wow, okay.
It confirms that the proposer's ability to generate relevant, learnable tasks is fundamental. The bottom line from these ablation studies is really clear. All the key parts of AZR, the different reasoning types, the proposer's learning mechanisms, they're all essential for achieving those strong general reasoning abilities.
So it really is a carefully balanced ecosystem of learning. Interesting. The paper also noted some patterns in the training process itself, something about the length of the outputs.
Yeah, an interesting observation. They saw that the solve role generally produced longer outputs than the propose role.
Longer solutions than proposals.
Which intuitively kind of makes sense, right? The solver is doing the detailed work of finding a solution, step-by-step reasoning, which often requires more output. The proposer is more focused on the initial, often more concise act of just generating the task.
Yeah, that tracks. Solving takes more explanation than just asking the question. Were there differences depending on the type of reasoning? Abduction versus deduction versus induction.
There were. They noticed a pretty consistent trend in the length of the solutions across the reasoning types. Abduction and deduction tasks tended to have shorter solutions compared to induction tasks.
Shorter. Okay. Why might induction need longer solutions?
Well, their hypothesis is that induction might sometimes involve a more exploratory, maybe even trial and error process. The model might be generating and evaluating potential inputs or rules, leading to longer explanations that kind of show that iterative thinking.
Ah, so it's showing more of its work for induction.
Possibly. And the researchers point out this is actually a novel observation, especially seeing it in models trained on multiple reasoning tasks simultaneously like this.
It's like the AI is showing its work in different ways depending on the task. Now, you mentioned earlier that the researchers flagged some issues. The paper talked about safety alarms ringing and uh-oh moments. That definitely sounds like something we need to dig into.
Yes, absolutely. While the overall results are very positive, they were careful to point out that they did observe instances where AZR, particularly when using the Llama 3.18 billion parameter model, occasionally produced concerning chains of thought.
Concerning how? Logical errors or something?
Actually, worse. They called them uh-oh moments and included an example figure in the full paper, that we don't have the specifics here. But the fact that they used language like safety alarms ringing suggests these weren't just minor reasoning slip-ups.
Right. That implies potentially problematic outputs.
Exactly. And they explicitly highlight this as a really important area for future work. The need to develop safety-aware training methods specifically for AZR.
That seems critical. As AI gets more autonomous in its learning, making sure its reasoning and outputs stay aligned with, desirable outcomes is absolutely paramount. Okay, so safety is a key future direction. Did they explore other ways to potentially improve AZR? I think you mentioned complexity rewards.
Yes, that was another interesting future direction they discussed. The idea is to potentially reward the proposer based on the complexity of the problems it generates.
Rewarding it for creating harder problems. Why?
The rationale is that the complexity of, say, a piece of code might be a good proxy for how challenging it is to understand its properties. For a reasoning learner, tackling more complex problems could lead to deeper learning.
Okay, but how do you even measure complexity in a way an AI could use as a reward signal? Seems tricky.
There are actually established metrics for this in software engineering. Things like cyclomatic complexity, which looks at the number of independent paths through the code, or Halstead complexity measures, which analyze operators and operands.
So establish ways to quantify code complexity.
Right. And the researchers mentioned experimenting with using these metrics, implemented through Python tools, as intrinsic rewards during the AZR self-play. The goal is to encourage the proposer to generate more intricate programs, potentially leading to richer learning experiences for the solver.
So rewarding the AI for challenging itself more, like encouraging a student to move beyond the easy stuff and tackle the advanced material. Now, AZR, this whole idea, it isn't happening in a vacuum, is it? This concept of AI learning through self-interaction seems like a bigger trend.
Oh, absolutely. AZR fits very neatly into this broader picture of self-evolution in large language models, or LLMs. There's actually a recent survey paper that lays out a nice framework for thinking about this.
Self-evolution?
Yeah, they frame it as this iterative process. The AI sets goals, creates tasks, finds solutions, gets feedback, and then updates its own model. It's an ongoing cycle of self-improvement.
And the idea is this is closer to how humans learn and adapt.
That's the connection they draw, yeah. And it's seen as key for enabling AI to tackle really complex tasks, especially in dynamic or changing environments.
Self-evolution. That's a powerful term.
Yeah.
What are some of the key abilities this kind of self-directed learning unlocks? The survey mentioned planning, I think.
Yes, planning is a big one. The ability to think ahead, strategize, create a sequence of actions to achieve a goal. An AI that can plan effectively can analyze a situation, predict outcomes, and develop a roadmap.
So it moves beyond just reacting to immediate inputs towards developing longer-term strategies. How does this self-evolution actually happen? The survey broke it down, right? Gaining experience, refining it, updating.
Exactly. That experience acquisition piece is where things like AZR's self-play fit perfectly. It covers how the AI creates and evolves tasks, how it finds solutions, and sometimes how it gets feedback from its environment. Task evolution in particular is super relevant to AZR, the LLM designing and refining its own learning tasks based on its goals.
And there are different ways LLMs decide which tasks to work on. It's not always just random sampling.
Correct. Some methods do use random sampling, but others are more strategic. You might see approaches that select tasks specifically for diversity to ensure a wide range of learning. Others might focus on breaking down a big initial training set and tackling smaller pieces sequentially.
So different strategies to make sure the AI gets a well-rounded education, so to speak. What about when the AI can actually interact with the outside world, like running code it wrote or acting in a simulation?
Right, those are what the survey calls interactive methods for task evolution. Models can generate code, run it, see if it works, and use those results as feedback to improve.
Makes sense.
Or in embodied AI, like robots, the AI learns by interacting with its physical surroundings, cause and effect. There are even systems focused on the AI creating its own plans from scratch and using feedback from the environment to refine those plans over and over.
Getting that real-world feedback loop seems incredibly powerful, very direct learning. The survey also mentioned perturbative methods. That
Yeah.
sounds disruptive.
Hey, yeah, it does. These methods intentionally introduce changes or perturbations to generate examples of what not to do, incorrect solutions, or maybe even harmful ones in a controlled way.
Why would you want the AI to generate bad examples?
The idea is that by learning to distinguish these negative examples, the model's understanding of what is correct or desirable becomes much stronger. It sharpens its judgment. This also ties back to safety generating, and learning to avoid harmful outputs is crucial.
Okay. So learning from bad examples in a controlled way helps it better understand what good looks like.
Got it. So after the AI has these experiences, good or bad, and comes up with solutions, it needs to refine them, right? Decide what's worth keeping.
Exactly. Refinement involves evaluating and filtering the generated experiences. This can happen using specific metrics.
Like scoring systems.
Right, using external criteria or feedback signals to assess the quality. Like a reward function might score generated code based on correctness or efficiency. Filter out the low-scoring stuff.
Okay, so filtering based on scores. What about more qualitative approaches? Those involve a more in-depth evaluation, often through critique. The critiques can be generated by the model itself, self-critique, or they can come from interactions with the environment. Based on that feedback, the AI can then refine its solutions or even refine its approach to generating future solutions.
Self-critique.
Yeah.
Interesting. That sounds like a more nuanced way to improve. And finally, there's the updating stage. How does the model actually bake this refined learning into its core knowledge?
Updating often uses replay-based techniques. The model revisits past experiences, the good ones it kept after refinement, to reinforce learning and prevent forgetting, like a student reviewing notes before an exam.
Experience replay. Okay.
Some systems also use external memory to store past experiences or reflections, allowing the AI to draw on a wider range of its learning history when making decisions or learning new things.
It's like the AI is building up its own personal library of knowledge and experience. But the survey also warned about downsides, right? Relying too much on self-generated data.
Yes, that's a really important caveat. There are definite concerns about things like reduced linguistic diversity if the model only talks to itself, and this phenomenon called model collapse, where the model's performance, or just the variety of its outputs, degrades over time because it's primarily learning from its own potentially flawed or limited creations. It can kind of get stuck in a loop.
Like an echo chamber.
Sort of, yeah. It highlights the need to find a good balance between using this powerful self-generated data and grounding it with real-world data to maintain robustness and avoid these pitfalls.
So self-evolution, super exciting, huge potential, but also complex and needs careful handling.
Yeah.
Now, AZR uses self-play, and self-play is also a massive deal in another major area of AI reinforcement learning beyond just LLMs.
Oh, absolutely right. Self-play has a long, very successful history in reinforcement learning, especially in the world of games. The core idea is identical. Agents learn by interacting with copies of themselves or maybe with past versions of themselves.
We've all heard about it beating humans in board games. Where else in the broader RL field has self-play really made a mark?
It's been incredibly effective across various domains. Board games, obviously, but also card games like poker and a huge range of video games, especially complex strategy games. It's a core component in many multi-agent reinforcement learning systems, MRL.
And I gather there are different flavors of self-play algorithms in RL. It's not just one technique.
Correct. You can broadly categorize them. There are traditional self-play methods, then a series based on something called policy space response oracles, or PSRO.
PSRO.
Or methods that involve ongoing training as they play, and approaches based on regret minimization techniques. Each category has its own way of managing the interaction between the learning agents and updating their strategies or policies.
Could you maybe give a quick example from a couple of those categories?
Yeah.
Just to illustrate the differences.
Sure. A basic traditional example is just vanilla self-play. An agent plays against itself, over and over, updating its policy based on the outcomes.
Simple enough. What about PSRO?
The PSRO family is more complex. It involves maintaining a whole pool of different strategies learned over time. In each iteration, it tries to find the best response strategy against the current mix of strategies in the pool, and then adds that new best response to the pool. It builds up a diverse set of good strategies.
Maintaining a population of strategies.
Exactly. Then you have ongoing training methods that continuously update policies during play. And regret minimization approaches, like vanilla CFR, which are very big in poker. They focus on minimizing the difference between what the agent got and what it could have gotten by playing differently.
Different approaches for different needs. The paper also mentions the ELO rating system, like in chess.
Yeah, ELO is often used in self-play research as a way to track the relative strength and progress of the different policies or agents being trained. See how they improve against each other over time.
Okay, so a whole toolbox of techniques for leveraging self-interaction in RL. You mentioned specific game types earlier. Board games like chess and Go seem like the classic examples.
Absolutely revolutionary there. AlphaGo, and especially its successor AlphaZero. These systems achieved superhuman levels of play, and the key thing about AlphaZero was it learned entirely through self-play, starting with just the rules of the game. No human expert knowledge, no historical game data, just self-play.
That really was a watershed moment. What about card games? Poker? Maybe? That seems harder because of the hidden information. You don't know the opponent's hand.
Poker, especially No Limit Texas Hold'em, is definitely a huge challenge because of that hidden information, the bluffing aspect. Self-play is still crucial, but it needs help. Techniques like abstraction are used, simplifying the immense number of possible game situations and betting options into more manageable categories, and also continual resolving, where the AI recalculates parts of its strategy during the actual game based on the actions it observes.
Adapting on the fly.
Exactly. Systems like DeepStack use neural nets and continual resolving effectively. Libritis, another famous poker AI, used self-play to build a core blueprint strategy and also had a clever mechanism for self-improvement during matches against humans. More recently, Rebel incorporated ideas about opponent modeling beliefs about their hidden hands into a self-play framework.
It sounds like self-play, combined with other clever techniques, has been essential for cracking these complex strategic games. What about really complex team games? MOBAs like League of Legends or Dota 2, massive teams, real-time chaos.
Yeah, MOBAs are another level of complexity. Teamwork, coordination, incredibly fast strategic decisions. Self-play has definitely been applied there too. There was a notable example, WeKick, an AI that used self-play and actually won a competition against human teams in a MOBA game variant.
Wow. So across this really diverse range of games, self-play keeps proving itself as a remarkably effective learning mechanism. But it's not perfect, right? The survey mentioned limitations.
No, definitely not perfect. Some key challenges remain. One is the risk of converging to suboptimal strategies.
Meaning
Meaning the agents find a way to play that's good against each other, but maybe not the absolute best strategy overall, or maybe vulnerable to a different kind of opponent they haven't seen in self-play.
Getting stuck in a local optimum.
Exactly. The other major challenge is computational cost. Self-play often requires just a massive number of simulated games, and managing large pools of strategies, like in PSRO, can be very demanding.
Those sound like significant hurdles. So what's next for self-play in RL? Where is the research heading?
Well, future research is definitely focused on tackling those challenges, developing methods to maybe guarantee convergence to better strategies, or at least escape those local optima, and making self-play much more computationally efficient.
Makes sense.
There's also, as we've been discussing, huge interest in integrating self-play more deeply with large language models, building on things like AZR. And of course, exploring more real-world applications beyond just games.
It really feels like we've come full circle now, connecting self-play in general, RL, right back to AZR and its whole zero data learning paradigm, which brings us back to the significance of that absolute zero aspect. I know this even prompted a question online on Reddit.
That's right. And the Reddit comment you mentioned highlights a really crucial point of clarification. While AZR is called zero data, it's important for listeners to understand that it doesn't mean starting from a completely blank, untrained model.
Right. It uses a pre-trained base model like Llama 3.
Exactly. The zero data part refers specifically to the fact that for training its reasoning abilities in areas like math or code, it doesn't rely on any pre-existing, human-verified pairs of problems and answers. Those specific training examples are generated entirely by the model itself through the self-play process.
Okay, so the base model provides the initial foundation, language understanding, world knowledge, etc. And then the self-play mechanism refines and enhances its reasoning skills without needing external labeled reasoning data for those specific target domains.
Precisely. It learns to reason by reasoning about problems it creates itself.
And the Reddit user also made another important point. Stronger base models are probably going to benefit more from this approach, right? Which could potentially widen the gap between labs with huge resources and those without.
That's a very valid and important societal consideration. If a more powerful starting model is inherently better at generating effective self-play scenarios and learning from them, then yes, it could absolutely lead to a situation where the gap in AI capabilities widens further. Something to watch.
Definitely. Okay. So this idea of self-play is clearly incredibly powerful. And we even have examples now of it being applied to something as fundamental and frankly difficult as evolving alignment in LLMs. That sounds like a fascinating application.
Yes, this is another really promising line of research. There's a framework called EVA Evolving Alignment, which frames the challenge of aligning LLMs with human preferences as a game, specifically an asymmetric self-play game.
Asymmetric, meaning the two players in this self-play have different jobs or goals.
Exactly. In the EVA setup, you have a creator model. Its goal is to generate increasingly informative or difficult prompts, guided by a reward model that captures human preferences. And then you have a solver model, whose goal is to learn to produce responses to those prompts that score highly, according to that same reward model.
So instead of just training on a fixed set of human-written prompts.
Right. The idea is to move beyond relying only on a static set of human prompts. The AI essentially teaches itself what kinds of questions or situations are most useful for learning to provide better, more aligned answers. It generates its own alignment curriculum.
That's clever. And did it work?
The results reported are quite remarkable, actually. EVA was shown to significantly boost the performance of standard RLHF algorithms.
RLHF, reinforcement learning from human feedback.
Right. It boosted those algorithms on various alignment benchmarks without needing any extra human-crafted prompts beyond the ones used to train the initial reward model.
Wow. So it makes the alignment process more data efficient.
Very much so. In one example, they showed it dramatically improved the performance of a smaller Google Gemma model, allowing it to actually surpass its much larger 27 billion parameter version on a tough benchmark, Arena Hard, and even match the performance of models like Claude 3 Opus in some cases.
That's a huge gain, getting that level of performance from a smaller model just by using this self-play alignment technique. And this improvement held up even on unseen prompts, right? Suggesting it wasn't just overfitting.
Correct. It seemed to generalize well. It really ties back nicely to this core idea of curriculum learning through self-play, the agent creating its own optimal learning path.
It seems incredibly effective. But did they run into any issues, like the diminishing returns you mentioned earlier with self-play?
They did observe that, yes. Similar to other iterative off-policy training scenarios, the performance gains tended to get smaller with more iterations of this creator-solver game.
Why does that happen?
It could be several factors. The self-generated data might become less useful over time as the solver improves, off-policy issues. Or maybe the initial reward model itself has limitations and can only guide the alignment so far. But they noted that EVA's generative approach still helped mitigate this compared to just reusing static data. They even experimented with adding a rewriter step in the solver loop, which seemed to help further boost performance in some cases.
Always tweaking, always refining. It's a continuous process. The paper also briefly mentioned regret minimization and maximization in this alignment context. How does that fit in?
Yeah, it's another way to frame the game. The solver is essentially trying to minimize its regret, the difference between the reward score it gets and the best possible score it could have gotten for a given prompt. Standard alignment algorithms like DPO implicitly do this.
Okay. And the creator?
The creator, guided by the reward model, is trying to maximize the solver's regret. It's trying to find prompts that really challenge the solver, expose its weaknesses, and force it to learn and improve. It's this continuous adversarial push and pull that drives both the prompt generation and the response generation towards better overall alignment.
A fascinating dynamic. Okay, this has been an incredibly insightful deep dive. We've covered absolute zero reasoning, self-evolution, self-play in RL, even evolving alignment. To try and bring it all together, what are the really key takeaways for us?
Well, I think the main takeaway is just the truly exciting potential we're seeing for AI models to learn and significantly enhance their reasoning abilities without needing that constant, explicit human guidance or those massive labeled data sets for every single task they master.
Right. Approaches like AZR really demonstrate the power of self-play, self-interaction as an engine for developing more general, maybe more adaptable intelligence.
And crucially, this isn't just theory anymore. We're seeing these techniques lead to state-of-the-art results in really complex domains, math, coding, and making promising strides in the vital area of AI alignment, too.
Yeah. It feels like a really active and fast-moving area of research.
Absolutely. There are definitely still challenges like the safety aspects we discussed and lots more to explore, but the advancements are groundbreaking. They point towards a future where AI might learn and evolve in ways we're only just beginning to grasp.
So as we wrap up, maybe let's leave you, the listener, with a thought-provoking question based on all this. Consider the really profound implications of AI that can define its own learning journey. What truly novel capabilities might emerge when an AI can decide for itself what it needs to learn and how best to learn it.
And as this field continues its rapid progress towards perhaps more autonomous intelligence, what are the key ethical or practical considerations we really need to keep front of mind?
Definitely a lot to ponder there. Thank you so much for joining us for this deep dive. We really encourage you to check out the research papers we've mentioned and explore this whole fascinating field of self-play and self-evolution in AI further. Think about how these advancements might shape the future of technology and, indeed, our society. Until our next deep dive,